So we see that from their time of arrival, we can identify these gamma ray bursts as coming from space. And that meant that these things really didn't need to be classified anymore. And indeed, to stop World War III in case the Russians got surprised by these things, probably was good to tell people about it. And so these objects were published in an astronomy journal in 1973 and caused a great deal of excitement.
Not for us, because we were both in primary school at the time, but astronomers get very excited about a new class of mysterious object. These are pretty weird, these strange flashes of gamma rays of all things coming from out in space. So immediately lots of smart theorists started coming up with ideas for where these things might come from. Weird and wonderful ideas in vast profusion. One idea, for example, was that these things were coming from fairly nearby, and it might actually be caused by collisions between, say, comets. We know planets don't collide on a regular basis in our solar system, but most of the comets in our solar system are out where we can't see them, what's called the Oort cloud, a hypothetical shell of comets about half a light year out, and maybe some of the comets they were smashing into one another and, wave one's hands, producing gamma rays somehow. Quite how you produce gamma rays from colliding comets, I'm not sure, given that comets are travelling at about walking pace, but...
Well, the good news is when you have no information, you can make up anything you want. So, another idea that came about is that neutron stars, which we knew existed in the form of pulsars, are thought to have sort of a hard outer bit, a crust, and there can be little mountains on those crusts. And if they were to rearrange those crusts, then you might expect that neutron stars through the galaxy would, when they rearrange the crust, might put out a bunch of gamma rays as well.
Yeah, you'd expect this would be an earthquake on a neutron star, and you'd expect because of the intense gravity that an earthquake would be very violent. It has the right sort of energy. How you get gamma rays out of that?
Yeah, who knows?
Yes, we'll just wave our hands and look goofy and hope you go away. Another possibility is we're looking at the formation of a black hole. We know that a big star dies, runs out of fuel, everything falls down, produces a black hole, and there's plenty of energy there, and maybe some of it comes out as gamma rays somehow.
So let's go through. I mean, the big problem is we don't know anything about these objects, right? We don't know how far away they are. So let's go and look at some of the energy considerations about these three ideas that emerged when they first came out. So Paul, why don't you like comets, why don't you look at comets and see if that comes together? And I like neutron stars and black holes, and so I'll look at those.
So, could smashing two comets together produce the amount of energy we're talking about? Now, what we know is the fluence we get from the gamma ray burst. Now, fluence is not quite the same thing as flux, but it's closely related. Remember, we knew flux was the amount of energy received per square meter per second. For gamma ray bursts, it doesn't make sense to use energy per second because the energy changes so much. So we just count the total amount of power received per square meter per second, and that's the fluence. So the inverse square law of fluence is equal to the total energy rather than the luminosity divided by 4 pi d squared. So the standard equation was flux equals luminosity over 4 pi d squared. In this case, flux and luminosity are both energy per unit time, whereas it's just energy and fluence, so no per unit time. Anyway, the fluence of a gamma ray burst, these bright ones picked up by the first satellites, is about 10 to the minus 7 joules per square meter. And could we feasibly produce that by colliding comets? Well, we believe that our solar system, as the Sun and planets, is surrounded by a cloud of comets, a so-called Oort cloud, which completely surrounds us in all directions, and it's about half a light year out, which is about 30,000 astronomical units. If there are comets out there, which we think there are in very large numbers, we don't normally see them. We do see them if every now and then one of them comes in very close to us. So let's say it's skimming past here at some enormous speed, v1, and then orbits out, orbit taking us typically 1 million years, or 10 million years, or even more. Now when they're close in, we can look at the nuclei, and we see the centre of a comet has a radius of about 10 kilometers. Therefore, it must have a volume of 4/3 pi r cubed. assuming they're a sphere. They're not going to be very spherical, but that won't be too far wrong. The mass is going to be the volume times the density. The density of comets is actually unknown, but let's assume it's about that of ice. It's probably a bit lower than that actually, but that gives us a rough estimate. So the mass equals volume times the density, which comes out as about 5 by 10 to the 15 kilograms. So that's the mass. Now we need to know how fast they're travelling. We know they're going very fast here, about 70 kilometers a second, so we see that. But they're not going to be travelling that fast when they're out in the Oort cloud. To work out how fast they're going when they're out here, rather than in there, we can use conservation of angular momentum. Conservation of angular momentum is mv times the r, where v is the perpendicular velocity, and that is always the same. So what this means is the initial values must equal the final values. The mass hasn't changed. The radius has gone from, say, 1 astronomical unit here to 30,000, so the radius has gone up by 30,000 times, therefore the velocity must go down by 30,000 times. So instead of 70 kilometers per second, it's 70 divided by 30,000, so the velocity went out there is about 2 meters per second. So the kinetic energy is going to be half mv squared for each comet, but we're assuming we're smashing 2 comets together, so multiply by 2, we get about mv squared. We've worked out the mass, we've worked out the velocity, and that comes out as about 10 to the 16 joules. So let's say that we release all that as gamma rays, which is unlikely. It's a bit hard to see how you could smash comets together at 2 meters per second, which is no more than walking pace, and get gamma rays out. Most likely you'd make a gentle crushing noise and warm them up slightly. But let's assume somehow we managed to turn it into gamma rays. How many would we see at Earth? So the fluence we observe is going to be the energy over 4 pi d squared, where d is 30,000 astronomical units, and if you plug the numbers into that, it comes out as about 2 by 10 to the minus 12 joules per meter squared, which is a lot less than the observation. Observation was 10 to the minus 7. So we're about 100,000 times out. So it really isn't going to work very well. And that's assuming all the energy comes out in the form of gamma rays, which it most likely won't. Probably can cheat though. We could bring them in, instead of 30,000 astronomical units, to only 3,000 astronomical units. In that case, the R has gone down by a factor of 10, so the velocity goes up by 10, so that becomes 20 meters per second. This has v squared, so that goes up times 100. And then this has gone down by times 10, so that is times 100. So instead of having a difference of 100,000, we've only got a difference of maybe a factor of 5 or 10 or so. And so if you bring it even closer still, it might even work. So if there was some hypothetical inner Oort cloud that was only 100 or 200 astronomical units out instead of 30,000, we've certainly never seen a comet from it, but that might do the trick just about if you get 100% conversion of kinetic energy into gamma rays, which seems unlikely. So, not completely impossible, but certainly looking pretty dubious, this comet theory.